In this video, I will introduce the main principle of the Monte Carlo method, also known as Monte Carlo simulations, and I will explain how we can use it to estimate the mean value of a random variable, and also how we can estimate the error probability of an experiment, or we can estimate the entire statistical distribution in terms of the cumulative distribution function of a random variable. The Monte Carlo method is a type of statistical inference method, which means that we have a random variable and we would like to infer some of its properties. In particular, from this random variable, we could generate a multitude of realizations. Let's call them x1, x2, and xl. And based on these realizations, which is some data that we can analyze, we can estimate statistical properties that this original random variable has. So based on realizations, we would like to determine properties of a random variable. And this is different from the previous video on estimation theory, where we were interested in estimating the realization of a random variable. We knew the distribution of it, but we were observing the random variable in a noisy environment. But now we are instead interested in estimating something deterministic, something that has to do with the properties of the random variable. And the special thing with the Monte Carlo method is that we generate many independent random realizations like this, and then we use them to estimate these deterministic properties that the random variable has, such as estimating its mean value or potentially its entire random distribution. Let us start with analyzing the sample average. Say that we have a number of independent realizations from a random variable, x1 to xl. So L is the number of samples that we have. And all of them are coming from the same random variable so that the mean value is the same. And each one also have a variance that is finite. That is an assumption we need in order to use the following result. Namely, that if we compute the sample average, so we take our independent realizations, xl, we sum them up for all of them, then we divide with the number of them in order to get the sample average. Then, as the number of independent realization that we have in the sum approaches infinity, then the sample average approaches the mean value, the statistical average. This is also known as the law of large numbers, and the important thing is that the variance is finite. Then this convergence will happen. But in practice, we will never have an infinite number of realizations, so therefore it's interesting to know how large is the typical deviation between the sample average and the mean value. It is easy to show that the mean value of the sample average is equal to mu, because all of the terms here in the sum have mu as its mean value. Therefore, the typical deviations are determined by the variance of this random variable. And for a finite L, if we compute the variance of this is equal to summing up the variance of these different terms, but then we also get the 1 over L term here that will be squared, and in the end of the day we get the variance of each of these samples divided by L, which shows that the variance is going down inversely proportional to the number of samples we have. And then of course if the number of samples goes to infinity, well then this term will go to 0. And therefore there will be no variations between the sample average and the true statistical mean value. But if we don't know the mean value but compute the sample average, we would like to know how far away is mu. And we can't know that exactly, but we can create a confidence interval. For example, the 95% confidence interval, which is defined like this. You take your sample average and you deduct some kind of error tolerance, and then you add some kind of error tolerance, and then you say that the true mean value lies between these two numbers with a probability that is larger than 0.95. Then we have a 95% confidence interval for mu. The main challenge is to actually figure out what this error tolerance delta should be. And in practice, this one also needs to be estimated somehow. So there is always going to be some approximations involved here. One way of approximating it is to consider the central limit theorem, which says that when we are adding up many independent realizations from the same random variable, at the end of the day, the sample average here will look like a realization from a Gaussian distribution, which means that the deviation from the mean value is Gaussian or normal distributed. And the useful property of the Gaussian distribution is that we know that 95% of all realizations are within 2 standard deviations from the mean value, which in our case means then that we should select this delta to be 2 times the standard deviation, which is the square root of the variance. If we put it in here, then we should take 2 times the standard deviation that we had from the original random variable and divide with the square root of the number of realizations that we're having. So we now know what delta we will get with a certain number of realizations that we are using when computing the sample average. And this is a starting point of the Monte Carlo method. For example, consider that we want to estimate the mean value. Then we select a certain error tolerance, delta, that is greater than 0, that we would like to have in our estimate. So we can accept that the deviation from the mean value is at most equal to delta. Then we figure out how many random realizations we need in order to achieve that error tolerance. So remember we had this expression here, delta was equal to 2 times the standard deviation of the random variable divided by the square root of the number of realizations. And if we know delta, we can figure out what L should be. We rearrange in the equation and we get this expression. L should be equal to 4 times the variance divided by delta. If we are generating that number of independent realizations, x1 to xl, then we can utilize them in the Monte Carlo method to get a good estimate of the mean value. In particular, we compute the sample average and we use this as our estimate of the mean value. So this is the essence of the Monte Carlo method. We are determining how many random realizations that we need from the random variable, and then we are computing the sample average based on those realizations in order to get the estimate of the mean value. And the Monte Carlo method can be utilized in other situations as well. One possible extension is that we would like to compute the average of not the random variable itself, but some function of it. Maybe we can't observe the kind of thing that we are interested in ourselves, but we can observe something that have a mapping to that, and then we can compute the expected value of that term. And how do we do that? Well, first of all, the expected value is an integral expression like this, where you integrate over all realization you can get, you multiply with the probability density function, and then here we have the function of x, and then we integrate over all realizations that x could have. And if we know the probability density function, we can compute this analytically or numerically. But the convenient thing with the Monte Carlo method is that it works even if we don't know the probability density function. We are just generating the realization that we want. Then if we would like to compute this mean value, we take each realization, we evaluate the function based on that realization, we sum them up, and then we take the sample average like this. So we can apply the same methodology. The only important thing is that we might need a different way of figuring out how large L will be in this case in order to get a particular error tolerance. I will now provide you with an example of this procedure when we have an exponential distribution for our unknown random variable and it has a mean value of 1. So what I'm showing here is the mean value versus the number of samples. And the blue curve is the reference curve because the mean value is exactly equal to 1 all the time. And the red curve here is one realization that we are getting of the estimate here, the sample average that we are computing. With one sample, with two samples, and then we're adding sample by sample, and you can see that this curve is evolving. And it varies up and down, but the general trend is that it becomes closer to the exact value. And we know mathematically that when the number of samples goes to infinity, it will overlap exactly with the exact mean value. The dashed curve here, or the shaded region, this is the confidence interval. And remember, it was the interval between the estimate that we have minus something and the estimate that we have plus the same thing here. And this is then the interval where we can be certain with 95% probability that the true value is in between. And what you can see is that this minus and plus term is going down with the square root of the number of samples. So that's why you can see that the interval becomes smaller and smaller. And then since it is centered around the sample average, it also moves up and down like this because we can't know exactly where the mean value is going to be. But all the time here, we see that the true value is actually inside this confidence interval. We can use the Monte Carlo method to estimate other things, such as the error probability of an experiment. So consider an experiment that results in either a success or an error. This experiment could be to transfer data over a communication channel, where we either have a successful decoding or an error in the decoding of the data. Since the experiment has a binary outcome, either success or error, we can use a Bernoulli distribution to model this experiment, to say that an error occurs with probability p, and in that case we say that the random variable that is producing these experiments outcomes is equal to 1. And when it's equal to 0, we have a success, and that happens with probability 1 minus p. The goal now is to estimate the error probability. One can also estimate the success probability. They are just one minus the other one, but we will focus on the error probability. And the Monte Carlo method then would be to generate L independent realizations. So we are running this experiment L times, and every time we are storing, did we have an error? Then we have a 1 here. Did we have a success? Then we have a 0. And then we have our random realizations here. Then we compute the sample average. So we sum them up and we divide with the number of samples, and this would be our probability of error estimate. What remains is to determine what L should be, and what we did previously was to set the particular error tolerance, and then based on that one we were computing a value of L. The problem is that error probabilities, particularly in wireless communications, can vary by orders of magnitude, and therefore it's not so convenient to set an error tolerance as an absolute number. But we instead would like to have something that, for example, is relative to the size of the true value. And one common rule of thumb that people are considering is to figure out what is the smallest error probability that we will be interested in measuring. For example, that might be 10 to the power minus 4 or something like that. And then we are considering that we would like to have a number of realization that is equal to 100 divided with that error probability. Why? Well, then we have enough realizations in order to observe roughly 100 errors. If we are having too few samples, we might never see any errors at all, and then we have a very lousy estimate. So this is a very useful rule of thumb. And here's an example of this. In this case, the error probability is equal to 1 minus e to the power minus 1 divided by some kind of signal-to-noise ratio. And this is typical in communication systems, that the signal-to-noise ratio is determining our error probability. So here I'm showing the signal-to-noise ratio in decibel scales along the horizontal axis and the error probability along the vertical axis. And notice that we also have a logarithmic scale along that one. The solid black curve that you can see underneath here, and which is particularly visible down here, is the exact curve computed like this. Then the blue curve is generated like this. We have for 0, 1, 2, 3, and so on for every integer number of the SNR in dB scale. We have taken 10 to the power 5 or 100,000 different random independent realizations of the experiment, and then we have computed the sample average. And then I'm plotting a curve based on that one. And you can see that down until we reach the point here where the probability is like 100 divided with number of samples, that is when this rule of thumb on the previous slide made sense, we have a rather close result. But after that we can see that the blue curve is starting to jump up and down around the true value. And then we have a much more rough estimate. In particular, when we are reaching 10 to the power minus 5, then one error will roughly occur among all of our experiments. And then of course it's very hard to say if it should be 1 or 2 because it's too few experiments in order to figure things out. So when you're showing a curve like this, you should probably stop showing results at 10 to the power minus 3, because above that one we will have reliable results, and below it we know that there is large uncertainties. One thing to be concerned about is also to avoid systematic errors when you are plotting something like this. The red curve here is an example of what can happen if you are not generating new random realization when generating each point on your curve, but instead you generate just 10 to the power 5 random realizations, and then you are changing the signal to noise ratio. So the same randomness is used on the entire curve here. And what happens is that in the beginning it works fine, but then after a while, when we start to see deviations, the curve looks much more stable. It doesn't jump up and down like this because it is the same randomness here. And this might give the feeling that you have a rather good estimate of the curve, even if it is bouncing a bit up and down, but actually it is deviating here. And this is deceiving. One should always generate L new independent realizations for each point of a curve that you are generating using the Monte Carlo method. Finally, we might be interested in not just measuring one property of the random distribution, but the entire statistical distribution. And for a random variable, the statistical distribution can be described by the cumulative distribution function. F of a here, which is the probability that the random variable x is smaller or equal to a. We can use the Monte Carlo method to estimate this entire statistical distribution, but we need to do it for each a value here separately. So we generate L independent realizations, but in this case we use all of them to estimate the entire function. And for each a value here, we are determining how many of our independent realization that is smaller than that particular a. So here we have something called the indicator function. This function is producing a 1 when x of L is smaller than a, and 0 when it is larger than a. So here we get zeros and ones, and then we are summing up for all of our realization and we divide with number of them. So this will give us a sense of this probability, an estimate of it, in a similar way as we were estimating the error probability before. For each point on this empirical cumulative distribution function, we will have a deviation from the true cumulative distribution function. The variance can be computed based on the fact that the indicator function here is taking each realization and turn it into a realization of a Bernoulli random variable, because we are producing 1 or 0. And therefore, the variance expression here will contain the CDF value multiplied with 1 minus the CDF value. So these are essentially the probabilities of getting a 1 times the probability of getting a 0. And then we divide with the number of samples, just as before. So the variance will go down inversely proportional to the number of samples that we are having. Here is a final example of this. The true cumulative distribution function that we are considering here for a Rayleigh distributed random variable is 1 minus e to the power minus x squared. So we show x on the horizontal axis and the cumulative distribution function here between 0 and 1. And the true value is this blue dotted curve. Then the red curve is the empirical cumulative distribution function, or ECDF, that we are getting from 100 independent realizations from the random variable. And the curve have a staircase behavior because we essentially are seeing our random realizations here every time it is showing up for a particular x value, then we are moving up one step on this staircase. And based on the expression for the confidence interval, we can figure out the confidence intervals here vertically for each point. And we see that they are varying up and down, and they are larger in some regions than in other regions, depending on the shape of the true CDF curve. And in this example, we only have 100 samples because we wanted to be able to see this staircase behavior. But when we increase L, the red curve will become closer to the blue one, typically. At least the confidence interval will be shrinking and the red curve will be inside of it with 95% probability. But we can still expect to see some deviations, for example in the lower or upper tails, because we are seldom getting random realization that are showing up in those parts. In summary, the Monte Carlo method is based on generating L independent realizations of a random variable and compute the sample average of those realizations or some function of them in order to estimate statistical properties. And it's very important to select the right number L of realizations in order to get the right accuracy. And some examples of the use cases is to estimate the mean value of a random variable or the error probability of an experiment, or to estimate the entire empirical cumulative distribution function of a random variable that is providing a close approximation of the true cumulative distribution function that describes the entire random variable.